Gears are found in many types of equipment in which something moves. Basically, gears transmit power from one machine to another. When there's a gear problem, everything can come to a stop. Because of this, it's important for you to understand how gears work in order to keep them and their associated equipment operating. Basically, gears are used to transmit mechanical power from one device to another. When two or more gears mesh together, the arrangement is called a gear set or a gear train. Also, each gear is generally attached to a shaft. Often, gears that are meshed together will be of different sizes. In this case, the smaller gear is referred to as the pinion, and the larger one is simply referred to as the gear. Now, the way in which gears transmit power can be described in terms of speed and torque. Basically, torque is a force which produces or tends to produce rotation. Combinations of gears of different sizes can be used to change the speed and torque that is transmitted from one part of the machine to another. For instance, when two gears of different sizes mesh and rotate, the pinion will turn faster and with less torque than the larger gear. In this example, a pinion with 18 teeth is mounted on a motor shaft and is meshed with a larger gear that has 54 teeth. During operation, the pinion makes 3 complete revolutions for each single revolution of the larger gear. This relationship in which the gear turns at 1/3 of the pinion speed is a result of the number of teeth on the pinion and the larger gear. This relationship is called the gear teeth to pinion teeth ratio, or simply the gear ratio. This ratio can be expressed as the number of gear teeth divided by the number of pinion teeth. So in this example, since there are 54 teeth on the larger gear and 18 teeth on the pinion, there's a ratio of 54 to 18, or 3 to 1. This means that the pinion is turning at 3 times the speed of the gear. Now, often, more than one gear set is used in a gearbox. Multiple gear sets may be used in place of one large set because they take up less space. However, the gear ratio can still be used to determine the output of a gearbox. Let's see how. This illustration consists of 2 gear sets. This gear set has a pinion with 10 teeth and a gear with 30 teeth. The second gear set consists of a pinion with 10 teeth and a gear with 40 teeth. In our example, this shaft is turned by an external device, such as a motor, and is called an input shaft. This shaft is connected to and drives a machine such as a pump or a fan. It's often called the output shaft. This shaft, which connects the gear in the first gear set with the pinion in the second gear set, is called the intermediate shaft. Now, by using the gear ratio formula we looked at earlier, we can determine the ratio across the first gear set is 30/10, or 3 to 1, and that the ratio across the second gear set is 40/10, or 4 to 1. This information can be used to determine the ratio across the entire series of gears. That's done by multiplying the ratio of the first gear set by the ratio of the second gear set. So 3 to 1 times 4 to 1 results in a ratio of 12 to 1. This means that for every 12 revolutions of the input shaft, the output shaft will complete 1 revolution. Or in other words, the motor shaft is turning 12 times faster than the pump shaft. Well, so far we've looked at how speed can be changed across a gear set. And we've seen how this change can be described by using a gear ratio. These ratios can be used to help determine the speed of rotation of a gear set if the input or output speed of the gear set is known. Now remember, we said that the reason gears are used in machinery is to transmit power, and the way in which gears transmit power can be described using the equation power equals torque times speed. Now, we've looked at speed and how it's affected by the size of the gears. Now we're going to look at torque. You'll recall that torque is a force that produces or tends to produce rotation. The torque that's produced by a gear is a product of force and the gear's moment arm. The term moment arm stands for the distance from the center of the gear's rotation to the point at which force is applied. So, torque is a product of or equals the force that's applied to a gear times the gear's moment arm. This means that the longer a gear's moment arm, the greater the amount of torque that's produced for a given amount of force. So, in a gear set, the torque produced by the larger gear is greater since its moment arm is longer than the pinion's moment arm, and this increased torque is applied to the shaft connected to the larger gear. The change in torque across a gear set is referred to as the torque ratio. Now, from what we've seen so far, it may appear that gears are able to create energy in the form of torque. But gears, like everything else, must obey the laws of physics, which state that energy cannot be created or destroyed. It can only change its form. In other words, the energy or power that goes into a gear set must equal the energy or power that comes out of the gear set. This means that if power is constant and torque changes across a gear mesh, there will also be a corresponding change in speed. If torque increases, speed must decrease. And if torque decreases, then speed must increase. The relationship between power, torque, and speed not only describes what occurs across a gear set, but also explains why gears are used to transmit power. Gears are selected for particular jobs based on what the requirements are for either speed, torque, or both at the output of a gear set. For example, the next time you're driving to work, imagine what it would be like if you had to travel the entire distance in first gear. The gear ratio in this car is about 3.5 to 1 in first gear. You'd certainly have plenty of torque, but your top speed would be pretty slow. Or what if you had to stop at a stop sign while on a steep hill? Well, if you try to start up in fourth gear, you may spend the rest of the day at that stop sign. That's because the gear ratio in fourth gear is about 1 to 1. Your potential for reaching a high speed will be there, but there's not enough torque to get you going. Another gear arrangement would be more suitable in this situation. In first gear, you have enough torque to get you going again. This is a spur gear. Its gear teeth are machined or cut straight across. When two spur gears mesh to form a gear set, as shown here, the smaller spur gear is referred to as the pinion, and the larger gear as simply the gear. A spur gear set transmits power from one shaft to a parallel shaft, and is widely used in situations in which speed and torque are relatively low. In this arrangement of gears, the pinion and gear rotate in opposite directions. When it's necessary for two parallel shafts to rotate in the same direction, either an idler gear or an internal gear must be used. The idler gear is just another spur gear that is mounted between the original gear and pinion. The idler gear spins freely and transmits the power developed on the pinion to the gear. This way, the input shaft and the output shaft will turn in the same direction. Now, the other method that can be used to make two shafts spin in the same direction is to use an internal gear. In this example, the internal gear is also a spur gear. However, the internal spur gear's teeth are located on the inside of the cylinder instead of on the outside. In addition, the pinion is placed inside the internal gear. This arrangement allows the shafts to rotate in the same direction. The next type of gear we'll look at is called a bevel gear. Notice the difference in shape between it and a spur gear. Bevel gears are used to transmit power from one shaft to another shaft, which is usually set at a 90-degree angle. Other shaft angles are possible, but the most commonly used angle is 90 degrees. Now, if you were to closely observe a spur or bevel gear set, you would see that the gears mesh across the entire gear width at the same time. When gears mesh in this way, they may produce a lot of noise. In order to reduce this noise problem, and to enable the gears to carry greater loads, some spur and bevel gears are made with their teeth twisted. This design increases the surface area of the teeth and allows the teeth to engage more gradually. Since the teeth engage gradually, the noise produced by the gear set is reduced. And since the gear teeth are twisted, more gear teeth can be meshed at the same time. This increases the load that the gear set can transmit. Bevel gears made this way are called spiral bevel gears. Although spiral bevel gears are made differently from bevel gears, the two types are both used to transfer power from one shaft to another shaft, generally at a 90-degree angle. As you recall, a spur gear has straight teeth. A spur gear that is made with twisted teeth is considered to be a whole new type of gear called a helical gear. As two helical gears mesh, the contact between the two gears begins at one end of a tooth and extends gradually across the width of the tooth. This allows the gears to run quieter and smoother. This is also true for the spiral bevel gear. If the face of a helical gear is wide enough, several teeth will be engaged at the same time. This multiple engagement of gear teeth allows a helical gear to carry a larger load across a single gear set. Helical gears are normally used to transmit power from one parallel shaft to another. However, two helical gears may also be crossed to transmit power at 90 degrees. Helical gears are generally preferred over spur gears for high-speed operations because they can handle greater loads and they run smoother and quieter. Unfortunately, however, there is a problem associated with helical gears that needs to be addressed when these gears are used. The problem is that as helical gear teeth mesh, an axial thrust is developed along the shafts that support the gears. In other words, the gear and shaft try to move sideways. One of the ways to compensate for this thrust is to add a thrust bearing on the gear shaft. A thrust bearing absorbs axial thrust and holds the gear and shaft in the proper position inside a gearbox. Another way to compensate for the thrust is to add a second helical gear to the same shaft. This second gear's teeth are sloped in the opposite direction from the first helical gear, which acts to effectively cancel the thrust developed by the first gear. This arrangement is called a double helical gear. If this type of gear's right and left hands or sides are cut on the same cylinder, as shown here, the entire unit is referred to as a herringbone gear. There are herringbone gears in which a gap has been manufactured between the two sets of teeth, and there are other herringbone gears which are manufactured without this gap. Now, the last type of gear we're going to look at in this part of the program is called a hypoid gear. This is a typical hypoid gear. A hypoid gear resembles the spiral bevel gear in some respects. For example, hypoid gears are shaped like spiral bevel gears, and hypoids are used on cross-axis shafts like bevel gear sets are. But unlike bevel gear sets, the shafts of hypoid gears do not line up with each other. They're offset. This offset allows hypoid pinions to have as few as 5 teeth in a high-ratio gear set, while the various types of bevel gears typically don't have less than 10 teeth on a pinion. The smaller number of teeth on a hypoid pinion means that larger ratios can be obtained with a hypoid gear set than with a bevel gear set of the same dimensions. The gears we've looked at are some of the most common types of gears that are used, but keep in mind there are other types of gears as well. A worm gear set is characterized by one of its members having a screw thread. This part of the gear set is referred to as the worm. The other member of the gear set is called the worm gear, or just the gear. Worms are generally mounted on shafts, which are set at a 90-degree angle. Power is usually applied to the worm, which in turn drives the gear. The worm in a worm gear set is considered to be the pinion of the gear set. Because a worm has very few threads or teeth, a worm gear set has a very high gear teeth to pinion teeth ratio. Worm gear sets are generally used in situations where a large speed reduction with a subsequent large increase in torque is needed. Now, there are several different types of worm gear sets commonly used that you should be familiar with. Let's take a look at a couple of the most common. This is a single enveloping worm gear set. This type of gear set is one in which the gear is throated so that it wraps partway around the worm. The contact area, or mesh, between the worm and the worm gear is significantly increased by this arrangement and allows a larger load to be carried across a single gear mesh. Another type of worm gear set is the double enveloping worm gear set. In a double enveloping worm gear set, the worm is also throated so as to wrap partway around a throated gear. This arrangement further increases the contact between the worm and the worm gear. So this type of gear set can carry even larger loads than a single enveloping worm gear set of the same size. Now we're going to discuss some terms that are commonly used when working with gears. These terms include backlash, end play, and tooth contact. Let's begin with backlash. In order to explain backlash, we'll use this set of spur gears. Basically, backlash is the difference in size between the teeth on the gears and the spaces they fit into as the gears mesh. When the gears are at the tightest part of their mesh, a space usually remains between the teeth on the gears. The distance across this space is referred to as backlash. In other words, backlash can be described as the amount of space or freedom of movement that a gear has while its mating gear is held stationary. Gear meshes should always have at least some amount of backlash present. The reason for this is that backlash allows for thermal expansion of the gear teeth and for the proper flow of lubricant to the gear teeth. Naturally, though, different gear meshes will have different amounts of backlash. A gear manufacturer will normally specify how much backlash is acceptable for a given gear mesh. If you should ever find that a gear mesh contains too much backlash, it could be an indication of excessive wear of the gear teeth, or that the gears aren't close enough together. Backlash is just one term that's commonly used when working with gears. Another one is end play. End play is the distance that a gear and shaft are allowed to move axially, or along the shaft axis. We can use this illustration of a gear and shaft in a casing to see how end play occurs. When the gear is stopped, it is positioned as shown in the casing. As the gear is started and load is increased on the gearbox, the gear and shaft may begin to move axially. This difference in positions is the amount of end play. Just about all gears will experience some amount of end play during operation. In fact, some amount of end play is desirable. For example, a small amount of end play will allow the parts to expand when they heat up during operation. However, too much end play could prevent proper meshing of a gear and pinion and could cause uneven wear problems, overheating, and alignment problems. Severe cases of axial movement can even cause the gear teeth to break. End play can usually be adjusted by installing or removing shims from between the end caps and the bearing housing. The shims place the bearings, gear, and shafts in proper position inside the casing and controls the amount of end play by limiting axial movement. The manufacturer of a gear set will normally specify the allowable amount of end play associated with the gear set. Well, now that we've discussed backlash and end play, let's focus on another term that's commonly used when discussing the operation of gears: tooth contact. Basically, tooth contact is the area where gear teeth touch each other when they're meshing. Tooth contact may appear as a band of contact on a gear tooth. Ideally, this band of contact should be near the center of the gear teeth and parallel across the gear teeth, and fairly uniform from gear tooth to gear tooth. If it's not, it may be an indication of misaligned gears, which would result in improper tooth contact. Improper tooth contact, in turn, might cause excessive wear of the gear teeth. Many gear arrangements are enclosed in housings called gearboxes. Gearboxes also contain additional equipment that supports gear operation. This gearbox is used as a reduction gear drive for a conveyor. Basically, a reduction gear drive reduces the speed of the prime mover, such as a motor, to a slower speed required by the load, which in this case is a conveyor belt. This type of gearbox consists of an upper casing and a lower casing, which supports the gears and auxiliary components inside the gearbox. The lower casing also contains an oil sump, which holds the oil that lubricates the gears and bearings. An input shaft is connected to the motor, and an output shaft is connected to the conveyor belt. Finally, these are bearing end caps. Their job is to position the bearings within the gear casing halves. This gearbox is a double reduction type. It steps down the motor speed in two stages. The first stage of speed reduction occurs across this helical pinion and gear. The second stage of reduction occurs across this pinion and gear. The pinions and gears are mounted on shafts, which is supported by bearings on either end. The bearings are supported in parts of the casing referred to as the bearing housings. Spacers, or shims, are placed between the bearing housings and the end caps to properly position the bearings, shafts, and gears inside the casing halves. This gearbox uses wet sump lubrication. This means that the larger gears would be partially submerged in the oil sump in the lower casing. As the gears rotate, they would pick up oil from the sump and transfer it to the pinions. Part of the oil which is slung off the gears and pinions would collect in troughs in the lower casing. These troughs direct the oil to the bearings, and any excess oil in these troughs would overflow back to the sump. In addition to the one we just looked at, there are many other kinds of reduction gearboxes. They can vary with respect to their number of stages as well as the type of gears they employ. One of the more common uses for mechanical differentials is in the rear end of a car. When we look underneath this car, we can see the housing for the differential. The differential is connected to the drive shaft and the axles going to the rear wheels. When a car is driven in a straight line, the rear wheels rotate at the same speed, and the mechanical differential simply transmits power from the drive shaft to the rear axles. However, when a car is making a turn, the wheels rotate at different speeds. In this case, the differential still transmits power to the rear axles, while allowing the axles to rotate independently of each other. This mechanical differential consists of 3 bevel gears, a spider shaft, and a balancing block. These 2 bevel gears are mounted on bearings on the spider shaft and are free to rotate around it. This bevel gear is mounted to a balancing block on a bearing and is also free to rotate. The balancing block is attached to the spider shaft and rotates with it. The shafts that provide inputs and outputs are connected to the differential through these spur gears. Okay, now that we've identified its major parts, let's see how this arrangement works. When this shaft is rotated, the mechanical differential transmits power to these 2 shafts. If we continue to rotate this shaft and hold this shaft stationary, the differential continues to transmit power to this shaft. The same is true if this shaft is held stationary. As you can see, the differential allows these 2 shafts to move independently of each other. Okay, now let's see what happens when these 2 shafts are turned. As you can see, this shaft turns. As we've seen from this example, a differential can have multiple inputs or outputs. Another function that a differential performs that's less obvious is its ability to compare multiple inputs and provide a corresponding output. Right now, this differential is comparing the speed and direction of rotation of each of these 2 inputs and providing a corresponding output on this shaft. To get a better picture of how the differential compares inputs, let's change the speed and direction of rotation of these 2 shafts. We'll rotate this shaft at 500 RPM in a clockwise direction, and this shaft at 500 RPM in a counterclockwise direction. In other words, we'll provide inputs that are exactly opposite. Since the inputs are exactly opposite, they cancel each other out, and the differential provides no output. If we slow down this shaft, the differential now sees a difference in the input speeds, and the output shaft rotates. The output speed is proportional to the difference between the input speeds. Mechanical differentials are used in a variety of applications. We saw how they were used in cars. They're also used in many measuring instruments to mechanically monitor and compare rotation of equipment components. Many gear failures can be traced to one element that's common to most gear sets, and that's a bearing. Experience has shown that many reported gear unit problems resulted from bearing failure or damage. Bearings often fail due to lubrication problems such as contamination of the lubricant. Another common cause of bearing failure is gear unit overheating. This condition could be caused by a number of things. For example, overheating could be caused by a buildup of dirt on a gear unit that is cooled by radiating heat to the environment. A third reason for bearing failure could be that the unit was damaged when it was first installed or during subsequent maintenance. Another cause for failure could be that the unit experiences excessive vibration when it operates. A gear unit being out of alignment or position is another common cause of bearing failure because it places an additional load on the bearings. The malfunction of either the couplings between the gearbox and the prime mover or those between the gearbox and the driven equipment could be the cause of bearing failure. A failed coupling could cause excessive vibration to be transmitted to the gearbox and bearings. A failed coupling could also throw a gearbox shaft out of alignment. Still another reason for bearings to fail could be that either the prime mover or the equipment that's supplied by the gearbox is operating improperly. For example, a conveyor belt could be periodically overloaded during operation. This overload may be transmitted to the bearings in the gearbox and could damage them. All of the conditions that we just mentioned can lead to early bearing failure. And if a bearing fails, it can result in a lot of damage to the gears in the unit. One type of gear problem is gear tooth breakage. There are several ways in which a gear tooth or teeth can be broken. One way is through fatigue failure. Fatigue failure usually results from repeated bending or flexing of the gear teeth. Let's look at an illustration to see what can happen. The process of fatigue failure will be accelerated if some defect was present when the gear was manufactured, such as a tiny crack in the gear material. As the gear tooth passes through its mesh, the tooth is loaded and then unloaded. This loading and unloading process will cause the original defect to increase in size. And eventually, the defect will grow large enough that the gear tooth will break. When a gear tooth breaks due to fatigue failure, the appearance of the break will usually contain a circular pattern in the metal called an eye. During fatigue failure, a break slowly works its way across the tooth, and when the pressure gets to be too much for the tooth breaks off. Fatigue failures of gear teeth usually occur over a lengthy period of time, and they may be accompanied by what's called fretting corrosion. Fretting corrosion is set up as the gear tooth is loaded and unloaded. As the tooth is loaded, lubricant seeps into the defect and is compressed each time the tooth leaves its mesh. The combination of oil, high pressure, and a slight tooth motion breaks the metal down in the crack and erodes it. A reddish stain is produced as the metal breaks down. When a tooth breaks from a combination of fatigue failure and fretting corrosion, the break area will have a reddish stain. Now, even if the gear teeth haven't broken, you can tell when fretting corrosion is occurring by looking for this reddish-colored stain which seeps out of the defect in the gear teeth. A defect might be so small that it can't be seen with the naked eye. However, the reddish stain will usually be visible. The appearance of a break that has been caused by overload can be described as being rough. In addition, the gear tooth broken by overloading and the adjoining gear teeth may be deformed or damaged. and in some cases of overloading, all of the teeth on a gear may be deformed or damaged. An overload which causes a break may have been caused by forces external to the gear set, or it may have resulted from an internal force. It's important to be able to tell the difference between external and internal overloads because you'll deal with each type differently. Let's first discuss how internal overloads develop and see how to identify them. An internal overload starts when a gear tooth breaks due to fatigue failure as shown here. Then the adjoining teeth are overloaded as the mating gear teeth jump across the gap left by the missing tooth. This may cause the adjoining teeth to break. A close inspection of the broken gear in this case shows fatigue failure with a well-defined eye and adjoining teeth broken by overload with a rough appearance. A look at the crown or top portion of the tooth that broke due to fatigue failure indicates that the tooth was not deformed before it failed. This is also evidence that an external overload was probably not a factor. Now, if the fatigue break area contains a large amount of reddish stain, as it does in this example, then that indicates that the break took a long time to develop and is further evidence of an internal defect. There isn't much that you can do about breaks caused by internal overloads other than replacing the damaged gears. However, when you discover a failure that was caused by an external overload, you'll have to investigate the problem further. A first look at this damaged gear shows that a tooth was broken due to fatigue failure, and that the adjoining teeth broke due to overload. It looks very similar to the gear that failed from an internal overload. However, an inspection of the crown of the tooth, which broke from fatigue, reveals that it was deformed before it broke. This means that an external overload was applied to the gear set, which resulted in a break or a gear tooth already weakened by fatigue. When this tooth broke, the overload was increased on the adjoining teeth, and then the adjoining teeth broke. In the case of an external overload, a technician must not only repair the broken gear set, but he must also figure out what caused the overload and correct that condition as well. Some common ways in which gear sets are lubricated include using grease, using oil in a wet sump arrangement as shown here, or using oil in a dry sump arrangement. A dry sump arrangement is one in which oil is supplied to the gears under pressure. The oil is usually supplied by a pump. Some dry sump systems also have filters and oil coolers. Problems with lubrication or lubrication systems can soon lead to problems in a gear set. The basic cause of lubrication problems for gears include using the wrong lubricant, improper temperature, contamination, and insufficient lubricant. One type of gear lubrication problem can occur when the wrong kind of oil or grease is added to a gearbox during routine maintenance. The improper oil for a particular gearbox may not have the proper viscosity or oil additives to handle the loads, speed conditions, or temperatures that the gear set operates under. The use of the wrong type of oil or grease for a gear set results in increased friction and rapid wear of the gears. Heat can cause problems for gears when a lubricant does not remove the heat quickly enough. Heat damage can cause gears and gearboxes to distort, which can result in severe misalignment and damage. Overheating could be caused by a loss of cooling water flow to an oil cooler. Temperature may also become a problem if it's too low. If the temperature is too low, lubricant flow may become restricted, which robs the gearbox of its lubrication. Another lubricant condition that can cause gear problems occurs when lubricants become contaminated with dirt, sand, metal particles, sludge, or acids. Contaminated lubricants may cause a rapid erosion of gear teeth, which can cause teeth to break. The contaminant may also cause foaming of the lubricant, which can reduce the flow of lubricant to parts of the gear set, and this condition can reduce heat removal. You can prevent contamination from causing excess wear by replacing the lubricant at regular intervals. If a lubricating system does not lubricate all of the gear's tooth surface before they mesh, overheating and excessive wear may occur. Insufficient lubrication can be a result of clogged filters, clogged or improperly adjusted spray nozzles, or the improper operation of the lubricating system. Also, lubricant can be lost from a gearbox through a blown seal or a leaking joint. As you might guess, a problem that develops in a gear set's lubrication system may end up damaging the gears. Now, depending on the load in a particular gear set, this damage could occur almost immediately, or it could take some time to develop. One of the prime indications that a lubrication problem has occurred in a gear train is something called scoring. Scoring is a scratching or tearing of a gear's tooth. There are two general types of scoring that occur due to a lubrication problem. One is called initial scoring, and the other is defined as severe scoring. Let's take a look. Initial scoring appears as a fine etched pattern on the surface of a gear tooth. If the scoring has been occurring for only a short time, it begins as a band along the middle of each tooth and works its way out towards the top and bottom of the gear tooth. As we said before, initial scoring is usually associated with a lubrication problem. If initial scoring is found soon enough, it can generally be stopped by fixing the lubrication problem. Okay, now let's look at severe scoring. Severe scoring, as shown here, appears as heavy jagged tears in the face of a gear tooth. This type of scoring will continue if a gear set is placed back in service, even if the lubrication problem which caused it has been fixed. Severe scoring will eventually remove enough metal from a gear's tooth to cause the tooth to break. If severe scoring has occurred to a gear or gear set, they will probably have to be replaced. Another common type of gear problem that you need to be familiar with is pitting. Pitting may appear as either what's called light pitting or severe pitting on a gear's tooth. Light pitting appears as very fine holes or cracks in the face of a gear. Light pitting can be expected in a gear set as the gears age. Severe pitting appears as large holes in the surface of a gear's teeth, and severe pitting will eventually cause the teeth to break. Pitting is the result of a couple of different conditions. For example, it can be caused by a difference in the hardness of the metals used when gears are manufactured. Pitting that's caused this way is generally out of the hands of the technician. However, another cause of pitting, which the technician may be able to do something about, is misalignment. This helical gear was misaligned with its mating gear. Helical gears that are out of alignment will start to pit at the leading edge of the gear teeth. Pitting starts at the edge of the gear teeth because the load isn't distributed evenly across the teeth. It's concentrated on the edge. If the problem is not corrected, the pitting will gradually spread across the entire width of the gear teeth. Any gear set that begins to show more than light pitting during an inspection should have its alignment checked. And not only should the gear set itself be checked, but the prime mover for the gear set and the equipment being supplied by the gear set should also be checked to make sure that they're not causing the alignment problem.